All right, so in this video, we're going to talk about the cross product. In the last video, I know we talked a dot product. Now we're changing it up and we're going to a cross product. So we'll start with vectors v and w. And notice we're in R3 in this particular case. So for cross product, we'll be in R3. We've got our three components, v1, 2, 3, w1, 2, 3, and we will cross them. So v cross w. And so the way we would do this is actually setting up a 3x3 determinant. And so on the top row, we're going to have vectors I, j, and k. And then on the second row, we've got v1, v2, v3, w1, w2, and w3. And so to evaluate this determinant now, we're going to use the method of minors and cofactors. We're going to start with this row right here. That's the row that we're going to use. Generally speaking, you can pick any row or any column, but for these particular cross products, we're going to use the top row. And if you remember, the first step is to start right here. We cross out this row, we cross out this column. We'll have our I vector off to the side, and we'll have v2, v3, w2, w3 as our minor. So that's going to look like this, where we have v2, v3, w2, w3 with our vector I. Now, as you move over, this is associated with the negative, so that's going to be a minus. And if I cross out the row and the column that the j is in, I get a v1, v3, w1, w3 for the minor. So v1, v3, w1, w3 with our j off to the side. And then finally, for the k, if I cross off the row and the column, here's my minor right here. I've got a v1, v2, w1, w2, followed by our vector k. Now, if this process is new to you, you can always go back to my college algebra page and watch the video on evaluating determinants. That'll be quite helpful, but this is something that we're going to need to be doing a lot in this class, so if you need to go back and review it, please do so now. Now, one of the big takeaways from this is looking at the result. First of all, that is just a number. These are just numbers right here. So these are scalars. Scalar, scalar, and scalar. We've got a scalar now. We've got a scalar now multiplied by the I, scalar by the j, scalar by the k. This whole thing right here, when all put together, is going to result in a vector. So for a dot product, the result is a scalar. For a cross product, the result is a vector. Very, very important to remember that and understand that. So that's the basic setup for a cross product. I do want to look at an example, but again, if you need to go back and review evaluating determinants, then please go to the college algebra page and take a look at that. All right, so we'll go ahead and take a look at an example here. And I've got vectors v and w that are defined, and we're going to go ahead and cross v and w. So to get this set up, I'm going to have my I on top, then the j, then the k, then a 2, 1, negative 1, a negative 3, 4, and 1. And once again, using the ijk row, starting with the I cross this out. Here's that first minor. So we've got 1, negative 1, 4, 1 with an I. Don't forget the minus. So I cross out this with the j. I get 2, negative 1, negative 3, 1. So 2, negative 1, negative 3, 1 with the j. And then we've got our plus. If I cross out this and this, here's my minor for the k. So that's going to be a 2, 1, negative 3, 4 with the k. All right, so now we just have a bunch of 2x2s. We know that all three of these are going to come out to be scalars, though. So for that first one, we are going to have a 1 minus a minus 4 I. Then we're going to have a 2 minus a 3 j. Then we're going to have an 8 minus a minus 3 k. So remember, to get those, I multiplied this with this, minus this times this. This times this, minus this times this, this times this, minus this times this. So cleaning it up, that's going to give us a 5i, and then I'm going to have a plus, since that's going to be a -1 and a minus out in front, that's just going to be a j, and then I will have a plus 11k. So my vector 5, 1, 11 is the cross product of the two vectors. Now I don't care how you write it. I don't care if you write it like this or like this, but just to show you where it all came from, there is in fact the ijk vector as the result. Okay, so the result of a cross product is a vector. Now, I want you guys to pause the video and do something for me, okay? I want you to pause the video and I want you to compute W cross V, and see what happens there. So pause the video, work that, and then hit play again. All right, so you should have paused the video, worked that, and hopefully gotten a pretty interesting result. So when you did this, you hopefully ended up with -5, -1, -11, which is the same thing as a -5, 1, 11. So what you've learned is that cross products are not commutative. They're close, but they're not commutative. Dot products are commutative, cross products are not. And so that's going to lead us into talking about a few of these properties of cross products. All right, so now to take a look at these properties, you can find them on page 723. And you guys can take a look at those. They're pretty straightforward and easy to follow, but as I pointed out, some of them are different than some of the properties we've seen for the dot product. The dot product, for example, is commutative. So the dot product is commutative, but the cross product is not. And so this is number 3 out of that list, where it says that V cross U is equal to the opposite of U cross V. And that's an important one to remember as well, leading into this next theorem. So dot product is commutative, cross product is not. The theorem that I have up on the screen actually kind of summarizes this whole idea of what this cross product vector is. So if we have two vectors, V and W, in R3, then V dot V cross W and W dot V cross W both equal 0. So what does that mean? Well, if you think back to the dot product, if you dot two vectors and you get a 0, what does it mean? It means that the two vectors are perpendicular or orthogonal. So that means if we take this vector, right, this is a vector itself, and we dot it with V, that same vector, dot it with W, and we get 0, then what that tells us is that V cross W is perpendicular to both V and W. And that's really important. That's the whole driving force of this cross product. And so let me draw you a little picture here. So if we have, let's say, vector V right here, and we have vector W right here, then when we cross these two vectors, what we're getting is a vector, V cross W, that's perpendicular to both V and W. Now, circling back to up here, remember, it's not commutative, means you don't get the exact same thing, but you get the opposite of it. Well, what does that mean in terms of the vector? Well, the -1 would just be the one that points down, still satisfying both of those conditions. So this one down here would be a negative V cross W. Okay, so some very interesting results here coming from these cross products. And this theorem, in fact, is something that's upcoming on a future assignment.